Hi, I'm Atallah. I work at NXP Semiconductors, where I support the security certification of our MCUs and MPUs that will be integrated in connected devices. For such certification, we are using an evaluation methodology called SESIP, and I will now present what is SESIP and how it can be used in particular for compliance demonstration, for instance, to the RISC-V specification. But let's start with a bit of context. No need to remind that in IoT ecosystem, security has become a major topic. But maybe what is less known is that in order to address the security concerns in such ecosystem, many specification standards have been published in which you have security guidelines and requirements to be implemented by devices that have been defined. And the RISC-V Security Model Task Group is also currently working on its own security guidance. All those security guidance are made to raise the security level by pushing security by design, intrinsic security, which is fundamental. Now, having the security guideline defined is not enough. What is claimed also needs to be checked. And it is indeed more and more requested to prove that those security guidelines are well implemented. For instance, in Europe, the Cyber Resilience Act will make it mandatory for critical MCUs and MPUs to demonstrate compliance to a recognized standard. And you also have more and more schemes proposing a label to show end users the security level of devices. For instance, in US, labeling scheme is under study, and it's to be based on the NIST 8425. In Asia, you also have the cybersecurity labeling scheme in Singapore, which is already functioning, and based on compliance demonstration to the EN 03645. And there are many other examples all over the world of such regulations, labels, voluntary programs based on compliance demonstration to security guidelines. So this is important to be prepared and to have efficient tools to provide compliance demonstration, and that must be with a reasonable cost for developers. Because the thing is that those regulations and labeling programs are for full devices. But a device is not just one block, and the security requirements to be compliant with can be implemented in different components. So here you can see a high-level representation of a device composition, which have different levels of type of components, and at each level, several components. So this could be a RISC-V based platform. It could fulfill the RISC-V security model requirements, and also could be used to fulfill the device standards requirements to then comply with some regulations or labeling schemes as we have seen before. In NXP, we have already seen several of our RISC-V based platform compliant with several IoT devices standards. But NXP is a hardware component manufacturer. We provide the components to our customers, and those components will then be part of devices. And in fact, most of the device vendors do not develop all those components which implement the security requirements and are integrated into their device. So compliance demonstration to device security requirements cannot be done without the support of component developers. And also to mention, one component can be integrated in different platforms, different devices, and for different use cases. So the same component may need to prove compliance to different specifications and with a potentially high overlapping. So we can feel here already the complexity and the potential high cost and effort for developers due to a risk of repeating the same activities with no added value for the security. So there is this need for a methodology to be able to produce compliance evidence, taking the specific IoT context into account to optimize the efforts and costs and avoid unuseful repetition of activities which will be costly. And this is what the SESIP evaluation methodology of IoT platform addresses. So first, to be clear on SESIP role, SESIP is not itself defining security requirements to be implemented, but it has defined tools allowing to integrate and align security requirements from different sources. And it then produces, with one evaluation, outputs reusable as evidence of compliance demonstration to the different sources. Then if the same mechanism, for instance, secure storage features, need to show compliance to similar security requirements from several sources, SESIP allows the optimization of assessment activities. But also, as device is made of different components, SESIP allows the reuse of results from an evaluation into another one, which allows the assessment of the composition of several components. And potentially, components implement different security requirements. So maybe some are overlapping, some just adding to each other. But in any case, thanks to SESIP tools, this will be optimized and there will be no repetition. Let's see that a bit more in details to make it clear. SESIP allows the evaluation of components individually. For instance, RISC-V based hardware root of trust. This one will then be integrated with other components. This is a composition and this needs to be assessed, but all previous evaluation results at component level will be reused and only the integration aspects will be addressed. Plus, of course, it will integrate any unevaluated components, if any. You can have several compositions like this until reaching a full security platform. Then the device vendor will have all security evidence needed from integrated components to a final compliance demonstration to device standards. Now, this reusability is thanks to mappability of the external security requirements to the SESIP environment and vice versa. And this is possible thanks to the definition of a catalog of security requirements for connected platforms at an abstraction level, allowing this easy mapping to any external specification. So here you can see the list of the SESIP security feature that can be selected for a claim, because as a reminder, this is SESIP is not an implementation specification. This is not the list of security requirements to be implemented, but this is the list of selectable features corresponding to security requirements which have been previously defined by an external organization. Each SESIP feature is defined at a high level with simple wording, making it accessible to anyone without specific SESIP or evaluation expertise. As you can see, features titles are already very intuitive. Secure initialization, secure debug, secure storage, etc. And it is covering a large range of security requirements defined in most of current device specifications. Just as a note, in the next version of SESIP, additional features have been added to the catalog because they had been found missing. And this is the intent of this catalog, to be living. If some evaluation, some security requirements are found again missing, the catalog will be extended. Maybe a very brief focus on a specific set of requirements. A very important aspect to mention is that by default, SESIP takes into consideration only remote attacks and consider that no untrusted code can be loaded or part of the device. This is the default case, and only if another attack context is needed, for instance, local access to the device and or possible loading of presence of untrusted codes on the device, then the associated features must be claimed. And in the evaluation, the penetration testing will take the relevant type of attacks into consideration. This allows to cover only the attacks that are considered relevant to a specific device context, because not all products want to consider physical attacks. Typically, for domestic devices inside the private house, resistance to local attacks may not be relevant. So no unuseful assessment is done, and this is again an optimization of the activities, the effort, and the cost. Now, concretely, for RISC-V, if we take the security features expected from the charter of a security model task group, we can already roughly map the need to the SESIP catalog features. For instance, the root of trust can be a set of base security features. The secure boot is the secure initialization of platform in SESIP. The cryptographic requirements can be fully covered by the SESIP cryptographic features in the catalog. The unique identity is a mandatory feature in SESIP, mainly based on the secure identity of platform requirement. You also have the secure update, etc. Then about the type of requirements as tamper resistance and side channel. First, each SESIP security feature claim is responsible for its own asset protection, so it will be included in the feature. By default, it is against remote attacks, but as we have seen, it can also be added the need for resistance to physical attack, and the need for a different level of isolation or access control depending on the context. So this can be also used for the RISC-V mapping. And also in the next version of SESIP, there is a new type of feature to handle the verification of the application of environment processes that could be used for the requirements related to supply chain. And also at highest SESIP levels, there is a full set of evaluation tasks related to development environment assessment. Because indeed, the other base tool of SESIP is the definition of a catalog of evaluation tasks. And those ones depends on the SESIP level claimed. So the more the SESIP level is high, the more the confidence that the security claim is well implemented and robust must be high. And this is done by raising the amount of effort put into the security assessment, meaning more evaluation activities and more efforts. This is what you can see in this table. The highest is the level, the more evaluation activities you have, the more resistance of the product is expected. It starts with only the analysis of the developer security claims and the self-declaration in a document called security target, and verification against known vulnerabilities, published vulnerabilities. Then in SESIP 2, it adds third-party closed box penetration testing with additional functional specification information to be provided and analyzed. Then in SESIP 3, it's an open box penetration testing with, again, additional design and security architecture information, etc., etc. This until SESIP 5, with more and more developer inputs to be part of the vulnerability analysis. And this raises the confidence level that the target is compliant with the claimed requirements. Having those different levels allows optimizing the amount of efforts so it will be appropriate to the real need of security. To finish, based on those base SESIP tools, those catalogs of security features and evaluation activities, you also have the SESIP profiles. SESIP profile is the template for the minimum security claim features and evaluation activities for a certain type of products. For instance, there is the core MCUs and PU SESIP profile, which defines the minimum set of requirements to be implemented by root of trust. So it defines the very core features. It defines an optional extension with cryptographic features. It's optional because not all MCUs will implement heavy cryptographic operations. You also have optional extra resistance, physical and or logical with isolation, depending on the attack context to consider it. And an option is also to claim some feature into a secure enclave, which is isolated physically and or logically from the rest of the platform. And those features, they have been defined previously, as already said, after risk analysis by industrials. Which have collaborated to this profile. And this particular profile works perfectly with RISC-V based root of trust. NXP side, we have already applied this profile to some of our RISC-V based product. So it can be used. As a conclusion, we have seen that SESIP addresses this need for an efficient and optimized way of providing compliance demonstration to security requirements from several sources, and which will be more and more requested by regulations as the European CRA, the labeling schemes in US and in Singapore, and by many other cybersecurity programs all over the world. Another advantage of SESIP is that it's already in use. There is already a SESIP scheme which is issuing certificates, and those certificates are already recognized by some entities as the PSI verified scheme, by NIST for the compliance to the 8259A, which will be extended to the recognition of the NIST 8225 for their labeling IoT label. And there are many other recognitions under work, in particular with the ETSI EN 303645 already mentioned. And all that has been possible because SESIP is supported, maintained and promoted already strongly by many industrials. As a final conclusion, with all that, a SESIP certified RISC-V based platform can be used to show compliance demonstration to the RISC-V security module specification. And those evidence can also be reused for composition with other components and for further compliance demonstration to other specifications. That's it for my presentation. Thank you.